So, well, last talk of the day. So this is probably the only talk at the workshop on layer 2 solutions for blockchains. And this is based on joint work with Giulio Malavolta, Aniket Kate, Pedro Moreno Sanchez, and Matthew Maffei. So, I mean, the basic idea is that, I mean, everyone's sort of familiar with the notion that, there are layer 2 solutions out there for blockchains. You know, the most popular example of it being the Lightning Network, and there's the Raiden Network for Ethereum. So, I mean, there is some value, at least pedagogical value, definitely, to thinking about layer 2 solutions as a means to circumventing potentially some of the scalability concerns of permissionless blockchains, possibly even permissioned. And the essential idea is to, if Alice and Bob are performing a bunch of transactions all the time, they can essentially sort of, go off the chain and do their transactions. And once they've done their commitment, go back into the chain, and that way essentially just do one, transaction on the core blockchain itself. But the thing here is this is, most of the times, they might not have enough coins to lock each channel in this payment channel network. So essentially, you create a payment channel network, and if Alice wants to send something to Bob, it happens through a route that's created through a payment channel network. Now, the topology of this payment channel network graph is unclear, but you hope that it will be a strongly connected network for some definition of strongly connected, and it's going to allow transactions between any user pair. So this talk is, specifically focused on multi-hop, payments that you want to perform across this routing network, with a specific focus on being able to do this without leaking too much information about the transaction that's happening. What does this mean? Well, I'll elaborate a little bit more on it. The whole sort of payment channel network does have a strong relationship with Maurice Hurley's talk early in the week, where he presented this atomic swap and the escrow transaction. I personally happen to think the model of multi-hop payment channel networks is a clear restriction of the model that was presented earlier in the week during Maurice's talk. So the model I'm going to be talking here about specifically is that you're going to assume that you have a black box which does sort of a max flow algorithm and sort of determines a path with sufficient capacity for you to carry out a payment between Alice and Bob. So this is given to you. That's an independent question in itself, which has great interest. And there's been work on doing this using landmark routing at NDSS last year by Pedro, Aniket, and others. And what we are essentially trying to do is implement this multi-hop transaction with what we would call atomic semantics, all or nothing, right? Either this thing takes place and nobody in the middle loses money, or the entire transaction is aborted. And we're going to assume that this is sort of a synchronous channel, which basically means that if I don't get a message in this time period, I can safely assume that the participant is crashed, and I can either abort the protocol or go ahead with the appropriate steps. And in fact, this turns out to be like something fundamentally inherent to this specific model, where you've determined a path, and then you're trying to do this atomic transaction over it, because it places quite a few restrictions on even getting to an asynchronous solution. So yeah, as I said, a payment channel network enables multi-hop payments. So there's no need for a unique channel between each pair of users. And if Alice wants to send a payment to Kat via this intermediary, the question is, how do we do this? So there's already a solution in place in the Lightning Network for this. And the core idea is to use something known as a hash time lock contract. I'm sure most people are familiar with this. Essentially, this is an HTLC, or a hash time lock contract. It says that Alice pays Bob, in this case, 1 Bitcoin, if and only if Bob shows some X, such that h of X equal to Y before this time period of 30 days. And this 30 days thing is crucial here. So this is what brings the synchrony to the protocols that we are considering. So Bob can redeem this payment only with this valid pre-image of Y. So the question is, when this has to be done across, a path with multiple hops, how do we do this efficiently and ensure all or nothing semantics? So, the way HTLC right now is defined in the Lightning Network, Alice would define with Bob and HTLC, with a timeout value, say 30, pass this value along Y with the condition that the payment can actually be retrieved only if Bob is able to produce the pre-image that it will eventually be received from the sender. So Alice will go to Bob, the HTLC is set on that path between Alice and Bob, and then the HTLC is set with a smaller timeout value on the path between Bob and Cat. And once Cat has received this, Cat is going to provide the pre-image which was used to compute this hash and send it back to Bob. And if Bob is an honest participant in this protocol, he's going to produce this pre-image so that he can get back the payment from Alice. So it works perfectly fine in this setting. This is pretty much a rough model of how the protocol works within the Lightning Network. So there's one immediate problem that we can see because, as you can see, this is a well-determined path. Now, if the intermediary is malicious, then the protocol trivially doesn't have any liveness, right? On providing the pre-image, Cat sends it back to Bob, and Bob chooses not to participate in the protocol, and the protocol trivially stalls. Now, the trick here is that technically this is not atomic because Bob loses money. But what we are really looking for is that only the honest intermediaries don't lose money. So if Bob is malicious, and if Bob chooses not to forward the pre-image back to Alice, then it's Bob who loses money. The HTLC between Alice and Bob trivially times out, so Alice does not lose money, and Cat has already retrieved the money. So the protocol, and this is where the timing assumption really matters in the HTLC protocol as specifically defined by the Lightning Network for multi-hop channels. So every user in the path sets the outgoing payment with a timeout smaller than the HTLC in the incoming payment channel. And as I said, the most important feature that we're looking for is that the honest intermediary does not lose money. So if you think about the model, I mean, I don't want to step back on the talk by Morris, but in this model is a clear restriction of the model that was presented in the escrow transactions model. So what do we do? So what we had, as part of this work, what we are trying to do is try to understand the challenges for implementing atomic multi-hop transactions. And the crucial thing I'm going to focus on is enforcing privacy. And I'll sort of highlight what I mean by this in the next slide. So what we do is we define an ideal world functionality for payment channel networks, which precisely captures these definitions. So what we are really looking for is balanced security, which is this weak notion of atomicity, as I call it, where the honest intermediate users do not lose value. So at the end of this transaction, the intermediate user is back in a state as though he never participated in this transaction, so quote unquote. The strictly stronger condition is serializability or atomicity, which is to say that it's equivalent to some sequential execution. Now, why is this important? Because in reality, Alice, Bob, Cat, right? Now, Bob has another payment channel to some other process, and this is an arbitrary graph topology. So they all are getting transactions concurrently from, whatever their outgoing edges are. And so what you want to do is leave the state of the individual payment channels in the same state as it would have been from a sequential run of the same set of transactions. So that's what we call serializability. And additionally, what we are looking for is to make sure that the first thing that you observed in the sort of the core Lightning Network protocol is that the same pre-image, the same value y is transferred across the entire payment hop channel. So we want to get rid of this restriction at a core in this work. And we essentially formalize that using these properties where we say, okay, the off-chain Byzantine users do not learn any payment value, and you cannot receive the sender-receiver pair with high probability. So what does it mean? So in the sort of the classic multi-hop routing HTLC protocol that's done in the Lightning Network, it's the same Y which is used across the payment hop. So what literally the goal of this talk is to come up with a way to get rid of this Y. Can we make the HTLCs mutually independent of each other during this multi-hop protocol? So the goal is to enforce serializability and balance security and enforce this privacy and relationship anonymity property. And of course, we want to be compatible with the current version of Bitcoin, which in our case, we just need to make sure that we instantiate the hash function with SHA-256, and I think we're good. So the one core abstraction that we're going to need in any concurrent multi-hop payment channel protocol is a two-process consensus abstraction, which basically means that UI and UI plus 1 agree on the channel state so that they can decide which transaction is going to participate in a given execution. Because they're getting transactions from each of their out degree nodes, and so they have to reach consensus on which is the transaction that is going to be participating in a given round. But this is trivial to implement, two-process consensus between these two nodes. So in our case, our protocol is very simple. So what we do is at the start of an n-hop transaction, the sender will sample n many independent random strings, x1 to xn, and compute each yi as the result of applying this hash function to all xj such that j is greater than or equal to 1, but in an XOR combiner. And once we do this, so essentially, for instance, it's going to be for x naught, you're going to compute h of x naught and get y naught, and for x1 you're going to compute h of x naught XOR x1 and get y1. And the sender is going to provide the receiver with x naught, y naught, and the ith intermediary with yi plus 1, yi, and xi. And as with the standard HTLC model in the Lightning Network, the sender communicates these values to the intermediaries over an anonymous channel. And starting from the sender, each pair of neighboring nodes, UI plus 1, is going to define a standard HTLC on this yi plus 1, the value v, and with the timeout ti. You're still going to decrease the timeouts as you go across the payment channel. So what we're essentially doing is making sure that the release conditions on the contracts are uniformly distributed in the range of this function h, and so that the HTLCs of a single transaction are going to be independent from each other. Now, clearly, this idea will work as long as you can enforce this. You can enforce this well-formed notion on each of the intermediate Byzantine users participating in the protocol. And to solve this, what we basically do is leverage non-interactive zero knowledge. We compute the proof, and we also send that proof over the anonymous channel to the intermediaries. So that way, they can verify the well-formedness of yi plus 1, yi, and xi. So it's the same step as I described before. You compute the XOR combiner, and along with each pair xi, yi, you send the corresponding proof to the intermediaries in the receiver. So the sender provides the receiver with x0, y0, and the ith intermediary with yi plus 1, yi, and xi. And the intermediaries additionally receive the zk proofs to guarantee that yi is well formed, but without revealing all of the xi. So each pair of users is going to establish UI, each pair of users UI plus 1 is going to establish this HTLC. So far, so good? So, and the whole point of the proof is that each intermediate user can run the verification algorithm, and if the verification algorithm rejects the proof, you trivially abort the protocol. And there's nothing wrong at this point because the HTLCs will time out, and you're going to, nobody is losing money. You still enforce balanced security. You still enforce serializability. No information has been revealed about any of the intermediate state of the protocol. So whenever the condition for the, this protocol, it's essentially a two-phase protocol with this multi-hop atomic protocols. So at the point where you reach the sender, whenever the condition for the contract un minus 1 un is released, in the original protocol, it was just y. In this protocol, un can release xn such that h of xn is yn. And then un minus 1 can release xn minus 1 XOR xn, which is the valid contract for un minus 2 and un minus 1. And so this mechanism is going to propagate all the way across back the other direction in order for each of the intermediaries to claim back the payment. And as you see, no information is revealed about what is the actual hash value which is being transmitted, because each of these HTLCs are mutually independent. So in the more general case, so whenever the condition for the contract UI and UI plus 1 released, so somebody publishes a string, which satisfies the constraint that provides you the pre-image for that particular valid contract. So if you look at this trivial example with one intermediary, so you have x naught, which is h of x naught to y0, and h of x0 XOR x1, which gives you the value y1. And the proofs that are going to be computed are essentially what you're looking for, which is to check if there exists some x naught such that h of x naught XOR x1 is y1 and h of x0 is y0. And the soundness of the zero knowledge proof is essentially going to give us balanced security so that Bob does not lose any payment value here. And it also guarantees that Bob does not steal any payments. And so as you can see, this is a protocol that is seemingly very simple. It's compatible with the Bitcoin script, and it serves a purpose for enforcing privacy. So the protocol that I presented right now, I completely omitted all the local data structures that we are maintaining, how we are dealing with concurrency, and so on. So the point of this talk, what I wanted to stress is to sort of capture this trade-off between concurrency and privacy. So what is this trade-off? So if you think about it, as I said, this is a payment channel network. Each of these paths in the payment channel are getting requests from concurrent transactions with their out degrees. And so at any point of time, there are an unbounded number of transactions that they have to process. So what is the liveness property that we are typically going to get out of these protocols? Unfortunately, there's no trivial solution. So one thing that you can do is to say, OK, I'm going to block as soon as I see that there is a channel without sufficient credit. Or you can look for something more non-blocking, which is to say that, OK, if I have a set of transactions which are all conflicting on a given payment path, then at least one is guaranteed to make progress and terminate. So the question is, can we get non-blocking concurrency and still enforce these strong privacy properties? And it turns out that that's tricky, because to get some sort of non-blocking solution, we have to rely on some global shared state across the payment channels. So in our case, for the protocol that we present, we actually use global transaction identifiers, which is given to us as a black box in order to totally order these transactions. So if at some point I have two payments which are conflicting on a given payment path, in order to, instead of aborting the both of them, I wait and allow the transaction with a higher transaction identifier in order to go through and make progress while aborting only the other one. So that's the non-blocking solution that we present. And in fact, the non-blocking solution, so let me just give a quick example of why the blocking solution can lead to deadlock. So here you have a payment channel network, and I have a transaction from Alice to Gabriel and a transaction from Bob to Edward. So because no user has a complete view of the off-chain transactions in the peer-to-peer network, this is what can happen. So you have a transaction which starts from Alice, goes to Carol, and then from Carol it goes to Edward. Concurrently, at the same time, you have a second transaction, a payment operation, which is starting from Bob going to Fabi, and from Fabi going to Gabriel. And at some point, Gabriel is going to, this transaction is going to go over to Carol, and from Edward to Fabi. Now, the problem is, at some point, they have to conflict on the same payment channel in order for the other thing to go through. So what do they do at that point? So the most trivial solution is to just block, because you're in a deadlock situation. You're just going to block the protocol. So a non-blocking protocol, in our case, what we do is we maintain queues at each of these transaction identifiers. We check when there is sufficient capacity available for us to forward it, and then we allow the other transaction to make progress, the transaction with the higher identifier, instead of aborting both. So the non-blocking property essentially is to say that, OK, assuming everyone takes sufficiently many steps, and at least one process will make progress in a finite run of the system. So the intermediate nodes are going to maintain a current list of in-flight payment transactions and a queue of the payments waiting to be forwarded when sufficient capacity is available. And that's what gives us the true non-blocking solution.
What happens in this situation?
In which situation?
Now Carol would have to forward the blue payment to Edward, right?
Yeah.
And Fabi to Gabriel?
Yeah.
But you're saying there's not enough funds between Gabriel and Fabi?
Yeah. And so what you're going to do is wait and allow that, there's not enough funds for both transactions to go through, right? So what you're going to do is wait and allow the transaction with the higher identifier to go through. And that way, the other transaction is aborted. So there's not funds for both to go through, only one can go through.
Okay, say T1 has the higher transactions identifier.
Yeah. T2, yeah. In this case, T2, so we abort T1 and we allow T2 to go through.
But it never arrives.
Sorry?
Never arrives.
Which never arrives?
Smaller number that you're waiting for.
We assume that the set of transaction IDs is totally ordered. It's given to you. You can compare any two transaction IDs.
Somebody
No, this is a synchronous system. Assuming everyone makes sufficient progress, then the protocol guarantees progress that one transaction runs to completion. So you have to rely on the correctness of the processes. Otherwise, we can't give any liveness property. So it has to execute its protocol. So in fact, we can show something stronger. We can show that non-blocking solutions cannot achieve full anonymity, simply because you have to keep some shared state across the payment channels. So you have to keep some global state which is shared across the payment channels. And this global state leaks information. So you can't find a compatible non-blocking protocol while still getting a very strong notion of privacy. And as I said, the global identifiers leak the transaction ID to the intermediate users. And so this trade-off is something that we have to look at, and this seems to be something inherent to the payment channel model that we are looking at and which is currently adopted by the Lightning Network, because we first compute the path, we get a deterministic path between the sender and receiver, and it's just over this particular path that we work with. So if you have intermediate Byzantine users, there's no liveness. That's a trivial, that fundamentally follows from the model. And if you're looking for truly non-blocking solutions, then you have to keep some totally ordered state, which is shared amongst the participants in the protocol. So I'll just conclude with sort of some high-level overviews. So as I said, the first thing, really, right, with an HTLC, if you're setting a HTLC of 24 hours, and if the 24th hour Bob chooses to renege from the transaction, then you've essentially locked all the intermediate coins, and then there is no reason for a payment channel to go for a transaction to go through. And there are several essays on sort of HTLCs considered harmful, and what is the real way to get rid of this? One way to get rid of it is to get rid of the timing assumption that we are looking for, and have a more asynchronous protocol which leverages failure detectors to somehow try and understand if the transaction just isn't going through because the user is malicious or because there's just a network delay. The other option, and then there's always a question of more efficient solutions. There's a solution specifically for Ethereum at NDSS 19 this year, which I'm told is a lot more efficient, at least cryptographically speaking. The other sort of modeling question is to combine routing with highly concurrent payment transactions.
The Lightning Network, that is the detection model.
Yeah.
Applied to balance model as well? To account balance model, that's Ethereum, right? Seems your model is for the detection model and this solution is for the balance account model. I guess what I'm asking is whether your solution can be directly applied to account balance models as well.
You'll have to take me through the specifics of the account balance model.
What Ethereum does, the account and the balance is not the capsules of Bitcoin.
state channels.
Oh, state channels. I believe the NDSS 19 work does it. I haven't looked at it. I'm not part of it.
Yeah, how about your work?
No. As far as I know. I know Aniket can correct me, but I don't know. I haven't looked at Ethereum.
If you build a rider network, for example, can employ the rider, but not for the layer 1, right? Layer 1 is
Not.
Yeah, so layer 2 could be employed.
For Raiden?
I think the question was not about this. It was about more general state transitions. Like instead of doing a simple payment channel which starts.
So this is explicitly for state, for payment channel. It's not for state channel network.
Right.
There could be interesting ideas in that space, but not directly the way it's defined.
There have been implementations on Ethereum where you can do like a mixer over a payment channel. For example, on Ethereum, like maintaining like the properties that you mentioned.
I see. It's implemented in the Raiden network.
No, Raiden does not. Don't talk about Raiden. It's irrelevant. Like to this construction. More modern approaches towards doing multi-hop payments.
I see.
Implementing HTLCs.
But speaking of models, the other modeling question, as I said, is whether we can combine the process of routing with the actual transaction payment. So right now, as I said, you perform the route computation, you determine if there's enough capacity, and then you try and do the atomic protocol, which obviously has fundamental limitations because it places huge restrictions on the protocol liveness. But I guess more generally, there is this question of what is the just right Goldilocks model for us to work with for layer 2 solutions, assuming every blockchain going forward is going to need a layer 2 solution. Yeah.
Why should we stick to HTLCs for layer 2 solutions? Like they're very, very inherently harmful, as you mentioned, and based on Dan Robinson's talk also from January. There are other approaches to layer 2 which have the ability to plug privacy on top, where you have an aggregator of some sort that gathers off-chain transactions in a Merkle root, and this Merkle tree itself can be a Zcash style Merkle tree. So you can have privacy in this case, and you can have much better capital efficiency compared to HTLC based ones where in the worst case you have a bunch of capital locked up for so long.
I mean, so I guess with the HTLC-based solutions, in the synchronous case and with no failures, I would suspect they're a lot faster than these solutions. It's the only problem is when you're looking, when you have.
Assuming you find that out.
Yeah. Yeah, I don't know. I don't have a great answer to why HTLCs are the way to go forward.
Yeah.
Yeah.
It seems to me you're leaking a whole lot of information still through the timeouts and through, just by traffic analysis and work out the linkages.
I mean, you're talking about things like traffic analysis and sort of an external adversary being able to find out which that is true. Right now, the model is specifically focused on the protocol implementation itself while abstracting away time. But yeah, no, that is true. Any other questions?
All right. See you tomorrow morning. You need to be here at 9:30.